Okay, so today we would like to talk about sections 11.3, partial derivative. In section 11.1, we talk about a function contains two variables or more variables, and its definition. Okay, so for this, it's a function which contains not just only one variable, and we focus on two variables. If a function contains two variables, and so if we can see its graph is something like this form. I mean, it's a graph in three-dimensional coordinate system. Its graph is in three-dimensional coordinate system. Yeah. And then in section 1, it's something like the structure is something like the material in our first semester. First of all we talk about its definition, and after that we could consider continuity, and consider its derivative, and consider its property about derivation, and its property and its application. Yeah. But due to time, we won't introduce the continuity about this kind of function, the continuity. And one of the reasons is that it will be a little unrelated to another result. So for section 11.2, we could just skip it. Yeah, if we have more time, we could introduce some. Yeah, so now we talk about the derivative, but it has two variables. Now the function f contains x and y, two variables. So we want to know what does it mean. I mean, what does derivative mean? So we should come back. So now let's come back to single variable, y equals f of x. And y equals f of x, we want to know derivative. So we have a function, we consider a point A, and its y value is f of a. So this point is a of a. This point is a of a. And its derivative is defined by this way. We consider another point x, and consider another point its corresponding value. So it becomes f of x. So here the position is x f of x. So we have 2 points. So now we connect these 2 points. 2 points we could connect them, and it's a straight line. So it's a straight line. We have 2 points. So the difference in y is f of x subtract f of a. Difference in a, here we can see the triangle. So it's difference in y, and it's difference in x. So difference in y is their subtraction. Difference in x is their subtraction. This one. But it's a straight line, connect these 2 points. So but what we want is a tangent line, is in red color, this one. So we should consider let x approach a. Consider its limit. And it's exactly our definition about f prime a. Okay. Yeah, I will tell you the definition about partial derivative. But there is one important thing I should remind you. You should know it will be better to understand their structure. I mean, in the graph, what does it mean? It will be better to let you remind this result, let you memorize this result. Yeah, or this it's exactly meaning. Okay, so single variable, its definition is this one. F prime a is this one. So it's the derivative. Yeah, or you could say it also means this one. Here is our h. So difference in y, so it's f of a plus h subtract f of a divided by their subtraction h. and then h approach 0. H approach 0. Yeah. So it's exactly the definition about f prime a, f prime a. And once we have this one, we could define, we have a function f of s, we could consider its derivative function f prime x. Once we could define f prime a, so originally we just define derivative function at some point a, fixed, here a is given, given a, we consider its slope, the slope of this tangent line. F prime a means the slope. This tangent line is slope. Its slope is f prime a. Its slope. The slope of this tangent line is exactly f prime a. Its meaning. Yeah. Okay. And now let's see the two variable case. So now it's what we want to know is this one. G equals f of xy. We have this function. G equals f of xy. It's a function contains two variables, and its graph is the plane. Its graph. I just say in general case it's the same. We define in the same way. But here I just tell you you could view it this way. It's a plane, and what does the partial derivative mean? Here, there is one thing you should know. We consider tangent line. We consider the difference here. There is one thing you should know. Here is the difference. Here is difference in y. Here is our difference in y. Here we could rewrite it is our a plus h, f of a plus h. This one. Yeah, this one. So here this part is delta y, this part is delta x, right? Delta y, delta x. Yeah, but we have the plane the plane. I mean, it's in the plane xy. But now it has two variables. If you want to know, you want to use the similar definition. You want to know its tangent line and its the slope of its tangent line. You should know what does tangent line mean, right? The big problem is we don't know what the tangent line mean, right? So you should fix a plane. It's something like in xy plane. It's 2k. I mean y equals f of s. If it's just single variable, just the plane xy plane. Just in the xy plane, we could say it's tangent line. In xy plane, we could say it's a tangent line. But if you have not fixed the plane, we don't know what does tangent line mean, right? So you should fix the plane. If you want to know the tangent line at some point. So now we consider the point is when xy equals ab, this point. We consider the point at here is the graph. So since it takes time to give the graph, so I graph it in previous. Now let me tell you the definition. Probably, let me see. Definition f x a b f. I think I could use this one. Its definition is similar. I write down this definition and tell you what does it mean. Okay. Here let's see. Okay, so first of all, we use this notation. We fix the point when x equals a, y equals is something like this one. We consider the given a, so we consider the point a. In this point a is tangent line. We consider it's tangent line, and consider the slope of this tangent line pass through this point a f of a, this point. Then its slope is exactly its derivative of the function f at the point a. And now we consider the point ab, this point x when x equals a, we consider the point when x y equals ab. We consider in that point, we consider its partial derivative. Okay, so first of all, its partial derivative, and with respect to x, it's called partial derivative of f, partial derivative of f with respect to x at the point AB. And this one is called partial derivative of f with respect to y and the point AB. Okay, this one. Okay, so let's see. Let me explain it. Here you could see that in this case we have two variables, but in this case we fix b. The y coordinate we fix b, right? So the variance is just in the x coordinate, right? So actually in this case, in this definition, there is one thing, it's important concept. In its definition, we fix the coordinate y. It should be equal to b. So we fix in the plane y equals b. We consider we fix the y coordinate value. We let it be b. Yeah, I explain in the graph later. But here I tell you the difference, and I will explain it soon. And in this case, the difference is here in y coordinate. Here is b plus h is b, but in x coordinate, both of them are x. So we fix the plane x equals a. And what does it mean? If we say the partial derivative of f with respect to x at the point AB, it means that here we have a plane g equals f of s y. It's the graph, and we consider the point x y when x equals a, y equals b, and originally it's in xy plane, so g value equals 0, and then we consider its value when x equals a, y equals b. We plug in the function f. So this point is exactly x coordinate is a, y coordinate is b, g coordinate is f of ab, right? This point, its position is this one. In three-dimensional coordinate system. Its position is this one. And then now, so in first definition, it means that we fix y equals b. So we fix the plane. It's the graph. It's a graph about the function g equals f of s y, right? And for all the point x y g, all the point in x y and the g equals f of s y, it's the graph of the function. It's the graph is this one, and the x y should be in its domain. Okay. But so we consider its graph and then we fix the plane y equals b. Then we will have the intersection. It's the intersection. It's a line. And this line, every point in this line, it belong to this plane y equals b, and it also belong to the graph. Okay, but all the point in this line, it has a common place. It has a common place. Its y coordinate value is b, right? Because it's in the plane y equals b, right? So in this plane, we could consider its tangent line, right? Its tangent line, and consider the slope of its tangent line. So in this plane, we consider its tangent line. Its tangent line, and for the tangent line of its slope. For the tangent line of slope. For this tangent line, its slope is exactly this one. Because in this definition, we fix the plane. Here you could see we fix y equals b, right? We fix. I have write down here. We could remind you again. We fix y equals b. So it's something that it just have the change. It has a change. It changes in s coordinate. It changes in s coordinate. So we fix the plane y equals b, right? So we define by this way. Yeah, here. Just in s coordinate we have some change. Just in s coordinate we have some change. So it's the partial derivative of f with respect to x at AB, this point AB. Okay. Yeah, so it's the plane y equals b. So here we could write its slope is called fx AB. It's slope. The slope of this tangent line. It's important concept. Yeah, you should know. It's the most important. Actually, it's the basic and the most important concept. Yeah, it's basic one. And how about this one? Partial derivative of f with respect to y at the point AB. It will be similar. If you know this one, it will be similar at this one. It will be similar. But now, with respect to y, so in y coordinate, we will change. But in s coordinate, we fix. And we fix at the point x equals a. So we fix the plane x equals a. So now we fix the plane. Here this point is a 0, 0, and this point is, I write down. It's fine. I write down here. This it should be here, right? So sorry. So here is 0, b 0. We fix the plane y equals b, and here we fix the plane x equals a. You could see here we fix the plane x equals a. So we have a plane x equals a. We have the graph. Then the intersection is the line. The intersection is this line. The intersection is this line. In this line, they have the common place. The common place is that all of their s coordinate value must be a. It must be a form. S coordinate value must be a, because it's in the plane x equals a, right? So in this plane x equals a, we could consider tangent line. Yeah, again, once we have a plane, we could consider the tangent line of the function at some point. So in this plane x equals a, we could for the line at this point, we could consider its tangent line. So we could consider, so it's something like tangent line is something like this one. It's our tangent line, right? It's our tangent line. And for the tangent line, its slope is exactly partial derivative of f with respect to y. At the point AB. And you could see that. Indeed, you could see that here we change in the y coordinate, but in x coordinate, both of them are a, so we fix. So indeed we fix x equals a. Okay, in this case we fix. Indeed we fix x equals a. Okay, x equals a. So it's f partial derivative of f with respect to y, and here is partial derivative of f with respect to x. So if we say f sub x, then our variable is x. Our variable is x. In other words, y is in the plane. We could view it as a constant, right? We could view it as a constant. Since our definition for derivative, partial derivative, we originally we just said in some point, for example, in the point AB. So we fix the y value b. If we consider f sub x, you could view y value as a constant b. But if we consider f sub y of AB, then our variable is y. So for x coordinate value, we fix. So it's in the plane x equals a. So you could view x coordinate is a constant a. So actually, you could view it as a single function. If we consider f partial y, f sub y, you consider f sub y, you could view x coordinate is a constant. So actually, we just have the variable in y coordinate, and here we just have the variable in x coordinate, because in y it's a constant. If we consider partial derivative, yeah. So that's why I say the concept is important. And the graph is, if you know the graph what it means, it will be better for you to understand the following result. Okay. Yeah. Okay. So now I give you the definition, and I will give you several examples to practice. Yeah, but before that, we still have one notation should tell you. Okay, so here I write down. Yeah, this section, partial derivative, is important, basic and important one. Since in the following, in section 11.4 or 5 or 6 or even 7, in the rest sections, you will always use partial derivative. So it's basic one. And it's something like when we say derivative, property about derivative, or property about the derivative their application. Of course, first of all, you should know the derivative formula. About each function. So that's why I said partial derivative is basic one. So you should know what that we mean. So now let me tell you the notation. We will use. And I will give you the example. So g equals fxy. Yeah, originally we have a notation. Here is our f partial x, f partial y. What's the? Oh, sorry, I forgot to write that. Here is our f partial y, ab. Okay, so if we say f partial y, then we fix. If we say f partial y, then we fix the plane x equals a. And if we say f partial x, its partial derivative with respect to x, then we fix y plane. Okay, yeah. So we have the notation f sub x, f sub y, but we can see for its function. Once we have the function, we could define for each point AB, we could define its partial derivative, and so indeed we also could define this function, right? Replace AB by variable xy. So indeed we have these two functions. these two partial derivative function. So for this function, we could consider its derivative again. So it's, yeah, and denote by this way. So it's just a notation. So I just write down the notation. F sub x y, f sub y x. This one. And sometimes we use f11, f22, f12, f21. Yeah, but we often use the next one. Here, f partial x, partial, so sometimes we use this one. Here, since the function has two variables, if you remember that if we have one function, we use the notation f prime x. But we also say that you could write it this way, dy dx. But in this case, we can see that when you just have one single variable, then we use the notation d derivative. But now it has two variables. But we just consider variable x. Here. So we use the notation. The notation is original. If we write down the alphabet A, B, C, D, E, then it's this one. So its reciprocal is something like this one. I mean, it's the notation. This one. Okay. So it's partial. It's called partial. So f is partial derivative with respect to x. So it's our fx. Oh, so yeah, sorry. So I forgot to write down the originally its notation. I mean, sorry, f x a b we also use the notation. Sorry, f sub x we also write this way: partial f partial x a b. Sorry. In the previous notation, I forgot to write down this one. And here is this one. F partial y a b, use this notation. Partial f partial y a b. This one. So yeah, so for this one we can see it's partial derivative again. So with respect to x again. Partial f partial x. This one. Yeah. And for this one, sometimes we use partial square f partial x squared and equals. And since the function is g, so sometimes we also use this one. So it's just the notation. But basic notation, you should know what it means. Here is our y. Here is our y. Here is our x. It will be senior. Partial y, partial x, partial x, partial y. So again, partial square g, partial y squared. Partial square g, partial y, partial x. Partial square g, partial x, partial y. This one. And so on. You could define self-derivative and so on. X, y, x, and so on. Define it like this way. Okay. For example, here is, and if it has several, and for example, if it contains more variable, for example, it's w, f of x, y, g. If it contains three variables, then you also could denote it by this way. It's the function we can. And one thing I should remind you, when we write down this form, the first derivative, the variable we consider its derivative is x. So we can actually means this one. We consider f sub x firstly, and after that we consider y variable its derivative. So you could see we consider f sub x, and after that sub y, right? Derivative, its derivative with respect to the variable y. And here it means f sub x, and after that consider y its derivative, and after that consider g its derivative. Yeah, this one. It's the notation. Okay. Yeah. So now we could write down. We could think about the example. I will tell you the example. Yeah, and for its, I will tell you the example. For the actually, we should practice more examples because but in the examples you will see that we will use our single variable function their derivative formula. Okay, so we will record the result in our first semester. Yeah. Okay, so now and here I write down example. We want to find the first derivative of the functions. The first one, fxy equals 4, subtract square, subtract 2y square. Second one, x cubed plus x squared y cubed plus subtract 2y squared. Third one, of xy equals sine of x over 1 plus y. Next one, x to the power of y. And more general is if it contains three variables. If it contains three variables, it will be similar as, for its definition, it will be similar. If we consider its x variable, its derivative, then we fix y, fix g. Okay? In some point, we fix, yeah. X to the power of y times g squared. And then next. Yeah, we should practice more examples. So here I write down the examples to let you practice. So of course, when you see this video, when you do some example, you should think about if I practice 2 or 3, then you could stop it and think about could you solve it by yourself. Yeah. Because it will be similar. But you should recall some single variable their derivative formula. So once you know one of the example exactly what it means, you will know all the result how to solve it. X squared y. Okay, we could practice more examples. And for these two, let me see. Yeah, okay, so here I erase it. Now let's see the examples. And before we, let me see. Okay, so before we consider this term, I think I could. Yeah, before we consider this one, I'll give you a quick example to tell you what's the difference. I mean, okay, so fs sub x ab is defined by this way. Limit h approach 0. Original is definition is this one. We consider the variable is x, so fix the plane y equals b. We fix the plane y equals b. So if it's defined in this way, its original is definition is this one. Of course, when you do this kind of function, this kind of problem, you don't need to follow the definition each time. But I will tell you the technique to solve it. But for the first example, we just follow the definition and tell you how you could solve it directly. Okay, so original is definition is this one. We fix the plane, right? So now we consider the function fxy. If we just consider the simple function x squared y, we consider a simple function x squared y, x squared times y, and the point is 1, 1. We consider 1, 1. We want to know this one and this one, and let's see how to solve it. If we just follow the definition, is 1, 1. So limit h approach 0. And here is h of f1 plus h1, this one. Subtract f of 1, 1, this one. So here is this one. You will see. Here the y coordinate all of them is 1, right? So it's exactly the constant, this one. So here, once we plug in the value, the function, you will get 1 plus h squared times 1, subtract 1 squared times 1, divided by h. This one. And here, all of them have the constant 1. Maybe it will be better to, okay, I change it. 1, 2, 1, 2. It will be better. Okay. So in this case, you will see all of them have the variable 2, right? So we could take out a common number. So it's limit h approach 0, h times 1 plus h squared subtract y squared times 2. This one. But it's just a constant 2. It's just a constant 2. So actually we consider its limit. This one, this limit, right? This limit. But this limit, what does it mean? It's exactly if we define a function g, defined by this way. G of x is defined by x squared. Then what's g prime 1? What's g prime 1? G prime 1 is exactly limit h approach 0 and what g of 1 plus h subtract g of 1 divided by h. And it's exactly g of 1 plus h, so 1 plus h is squared, subtract 1 squared divided by h, and its limit. Right? And it's exactly this form. So in other words, it's exactly this 10 is exactly g of x, its derivative at 1, when x equals 1, right? Okay, so actually when you consider for this function f of x1 x squared times 1, when you consider its derivative with respect to x, then at a point x equals 1, y equals 2, actually this one is exactly, here this 10 is 1 plus h squared times 2, here is 1 plus h squared, 1 plus h squared, sorry, it's 1 squared times 2. 1 squared times 2. So you could take out a common number, but for this 10, it's exactly, this one is g prime 1, it's exactly g prime 1, right? So when you consider its derivative, you could do it by this way. I mean, just consider for the value y, we put the value y, so it's 2x squared. So it's exactly, just consider this term is exactly x squared is derivative. X squared is derivative is 2x, right? G prime x is derivative 2x. So G prime y is 2 times 1. So G prime y is 2 times 1. So for this term, it's exactly G prime y is 2 times 1 times 2. This one, right? And then in general term, if you replace A1, 2 by AB, what's the result? What's this one? You will get it's just replace here its derivative is this one. And here we can say G prime 1. So now we replace 1 by A. So it's 2A times here for the value y. In this example is y equals 2, but general is b, so 2a times b, this one. And for every point AB, its partial derivative with respect to x is this one. So its function, the function is this one, 2x times y, right? So what could you see? You could see that, or for this function, x squared times y, what is its derivative with respect to x? When we consider derivative, its derivative with respect to the variable x, for the y variable we fix, it's something like a constant. Actually, we consider we fix a point. Originally, we fix a point. So indeed, it's a constant. So you could just view it this way. X squared is derivative. You could view y as a constant. It's something like just a constant. For example, in this case, it's a constant 2. It's constant 2. So you could view it as 2x squared. It's derivative. 2x squared is derivative 4x. And apply in the value 1. You will get 4. Right? Okay. Yeah. So when you consider the variable is x, then for the value y is a constant. We fix it. So you could view just as a constant x squared times, for example, is this one. We replace y by b, so it's x squared times b. So for this, so when we consider its derivative with respect to x, then indeed just fix y at some point b, so consider its derivative is actually 2x times b. So replace b by y, so it's this one. And similarly, when we consider partial, this one, what's this? Now for this one, it's this one, limit h approach 0. So our variable is y, so for x we fix it. So here we fix when x equals a. So its definition is f of a plus h. We fix a, so it should be fixed. And b plus h subtract f of ab divided by h, this one. Fix a. So when you consider its derivative, we fix a. So x squared is a squared. X squared is exactly a squared. So you could build a function as f of a y. So it's a squared y, this function. When you consider its derivative, you could build this function. So indeed, it's a single variable function because we fix a. The reason is that we consider the derivative is y. I mean, the derivative with respect to y, so fix x. So it's something like this function. And this function, its derivative is a squared, right? This function is derivative exactly a squared. For this function. So in general, fy xy is exactly y squared. This one. Oh, sorry, it's not. here is a squared times 1. Y its derivative is 1. Y its derivative is 1. Yeah, so here is s squared. In general, it's s squared. Yeah, just s squared times y. If you view s squared as a constant, then we just have the variable y, and y its derivative is 1. So s squared times 1. S squared times 1 is exactly s squared. Exactly I squared. Okay. Yeah. So now indeed we could practice the following result, the following examples. Okay.